In this lecture, we are going to discuss the microscopic and the macroscopic views of doing thermodynamics. So there are two different approaches to thermodynamics. So one comes from the microscopic approach, and this approach is called statistical thermodynamics, while the other one comes from a microscopic approach, and that is called classical thermodynamics. We are going to discuss the difference between these two approaches, and we'll discuss why we are going to go ahead and use the classical thermodynamics approach in this course. Any system that we want to investigate can be studied either from the microscopic viewpoint or the macroscopic viewpoint. Let's say, for an example, consider a tank that has 1 mole of helium gas. So this is composed of N equals to 6.02 into 10 to the power 23 atoms of this monoatomic helium gas. Now, if we want to define the state of this system, so we've not gone into formal definitions of what we mean by system, and that's what we are going to do in later lectures. But let's say if we want to define the state of this system, that is, we want to describe what this system is, and we want to describe the behavior of this system due to some changes that we impose to this system, then what we need to do is that we need to work with 6n variables. Why? Because we need to know 3n positions of the molecules or atoms, and also their velocities in 3 components. So 3 components of position x, y, and z, and 3 velocity components for each particle, and therefore 3n in all. Okay, so that means we need 6n variables to describe this system or behavior of this system if we were to use the laws of mechanics. So imagine that we know how these two molecules or particles interact with each other. If we can do that modeling, that how these particles interact with each other, then what we can do is that we have 6n variables to solve for, and we can get right equations for motion from laws of mechanics using these interaction forces, and then we can solve for the positions and the velocities of all the particles within the tank, and theoretically that is possible. But we are dealing with order 10 to the power 23 number of equations to solve for so many number of variables, and that's a hopeless task even for the best of the computers. Moreover, in practice, and particularly for even engineering, it is unnecessary to find positions and velocities of each of the particles, because when we do these measurements, we don't care about where different particles are. In fact, we cannot even measure the position and velocity of individual particles. What we are able to measure are some average properties. So we are able to measure properties that are average of large number of particles. To avoid using laws of mechanics, there are two approaches. So theoretically, from mechanics, I should be able to predict the state of this system, but that is not practically feasible. So that's why there are two approaches to reduce the number of variables and the corresponding equations. So even though mechanics would be good enough to solve theoretically this problem, but the problem is that practically you cannot do so. So we need to reduce the number of variables and the equations, and one approach is the statistical approach. So in the statistical approach, what we do use statistical considerations and probability theory to deal with average values of these particles, and this approach is used in statistical mechanics. And from this approach, we can arrive at different postulates of thermodynamics in the limit that you have large number of particles. But another approach, which is more practical from engineering point of view, is using the macroscopic viewpoint, which forms the basis of classical thermodynamics. Here, we deal with experimental or empirical measurements, and we do not care about the effect of individual particles, because from macroscopic point of view, when we perform these measurements, we are unable to resolve these individual particles. Now, for example, from a microscopic point of view, pressure that a gas exerts on a wall is due to the momentum that is transferred to the wall by these particles that are hitting at the walls. So the change in momentum of the molecules with the walls gives rise to pressure. However, from macroscopic point of view, we can simply measure this pressure using some pressure gauge. Therefore, in classical thermodynamics, we need to introduce new postulates, which we call as laws of thermodynamics, which are based on empirical evidence. And we treat these postulates as truth because there's no evidence that goes against these postulates. And using these postulates, we draw conclusions without considering the microscopic nature of the system. Now, both of these approaches, that is the statistical mechanics approach and the classical thermodynamics approach, have their own advantages. But the advantage of classical thermodynamics is that it does not depend upon the simplifying assumptions that we need to invoke in statistical mechanics. But there is another problem with classical thermodynamics, that we can, although relate properties of the substance with each other, but it is not possible to quantify that property using classical thermodynamics. So, not possible to quantify the properties. For example, later on we'll see, and you've seen part of it in your high school, that you have heat capacities at constant pressure and constant volume. So you can derive a relationship between those heat capacities using classical thermodynamics, but you cannot get the values of those heat capacities, let's say for an ideal gas. But statistical mechanics allows you to estimate the values of those heat capacities. Similarly, thermodynamics does not give you the equation of state. Let's say for an ideal gas, you have PV equals to RT, but you cannot get that from classical thermodynamics. You have to base that ideal gas relation based on the experimental measurements or empirical measurements. But from classical thermodynamics, you can arrive at the ideal gas law. So that's the difference between classical and statistical thermodynamics. But because engineering, eventually we deal with practical systems, and whatever theory we have should be able to match experimental measurements, therefore classical thermodynamics approach is what we're going to follow. But otherwise, both classical and statistical thermodynamic approaches, they both complement each other. Okay, but in this course, we are going to deal with classical thermodynamics. However, sometimes microscopic viewpoint can help in better understanding of certain concepts of thermodynamics, although we are going to stick only to classical thermodynamics approach. So, for example, how statistical approach or microscopic viewpoint is helpful is that from microscopic viewpoint, we know that thermal phenomena is due to disordered motion of particles, and this microscopic viewpoint is not invoked in classical thermodynamics. We now know from microscopic viewpoint that motion of these particles or disordered motion of these particles is related to heat So it comes out naturally that heat and dynamical energy are equivalent, because eventually you can describe motion of these particles using laws of mechanics for this particular system. But if you have to do the same thing for classical thermodynamics, you need to do experiments to show that heat and work are equivalent. And also for that we'll have to develop a postulate, and you're going to use that postulate later on in the course. So thermodynamics can be considered as, for this particular case, as a limit of mechanics of a collection of large number of particles, and such a large number of particles that detailed description of the state of motion loses importance, and only the average values or average properties become important. And note that we've seen that thermodynamics is not only applicable to mechanical systems, it's equally applicable to chemical, electrical, magnetic systems. So the idea is that you need to have large number of particles. So now, what do we mean by this average? What is this averaging? So whenever we perform macroscopic measurements, we say that these measurements are slow on atomic scale of time, and they are coarse on atomic scale of distance. What do we mean by this? We mean that, let's say you consider a metallic bar, and we want to measure the length of this metallic bar. So the characteristic period of vibration of the molecules or the atoms that are organized in this metallic bar is of order 10 to the power minus 15 seconds. But let's say the fastest measurement we can take is over, let's say, 1 millisecond, maybe by taking a snapshot of this metallic object. So what happens is that when we take measurement over time scales that are much larger than the atomic time scales, then what we measure is a time independent combination of the coordinates of atom, or we can say a time independent mode in which these atoms, let's say, move, and rest all modes in which these atoms behave or atoms move are averaged out, because we have taken our measurement over much larger time scale compared with the atomic time scale that is characteristic of the vibrations of these atoms. So only the time independent variable, which in this particular case is length, remains. Similarly, macroscopic measurements are also coarse on atomic scale of distance. For example, if we take a measurement with some optical means, then the smallest volume that we are going to probe, let's say this is a cubical volume that we can probe, is, let's say, about 500 nanometers, because that's the typical wavelength of light, and your resolution, let's say, for optical measurements is limited by the wavelength of light. On other hand, interatomic distance is about 0.5 nanometers. So in this small volume, you would have about 500 over 0.5, and that is in one direction, raised to power 3 number of particles or atoms. So that's about 10 to power 9 particles. So if you are measuring any property, what you're going to get is an average property, because you have such a large number of particles even in such a small volume. And therefore, the property that we are going to measure is an average of all these particles, which are large number of particles, and any fluctuation due to the discrete nature of medium is averaged out. So to summarize, macroscopic measurements lead to temporal and spatial averaging, that is averaging in time and space. Therefore, due to averaging that happens due to macroscopic measurements, we are left with a smaller number of variables to describe the system. So these variables can be, let's say for mechanical systems, these variables can be, let's say, length, volume. For electrical systems, these variables that we are left with are the electric dipole moment, and similarly for magnetic systems, we have the magnetic dipole moments. But we are going to focus mostly on mechanical systems in this course. So clearly, due to this averaging process, we have been able to reduce the number of variables with which we are going to work with. But in the process of averaging, we lose some information. What do we lose? We lose information about these hidden atomic modes. Because of macroscopic measurements, we do not know the microscopic behavior of the individual particles and the associated modes. But from microscopic viewpoint, we know that the energy transferred from these hidden modes or due to disordered motion is heat, whereas the energy that is transferred from the change of macroscopic variables is work. Energy transferred via work can lead to change of volume of gas in a cylinder, or can be extension of a rubber band. So that is mechanical work. Similarly, if there is a change in magnetic or electrical dipole moment, you can have energy transfer in terms of electric or magnetic work. But that work is related with change in macroscopic variables or macroscopic quantities that we can measure. But we've lost some information due to this averaging process about these hidden modes which correspond to heat. And to incorporate that loss of that information, we need some additional variables, and those variables are not known in mechanics or electromagnetism. So these are the additional variables that are required to describe the energy conversion processes, and these variables are introduced by the various postulates or laws of classical thermodynamics. The idea is that we work with macroscopic measurements and we work with variables or quantities that we can measure. But because we are ignoring the microscopic behavior in classical thermodynamics, we compensate by invoking new laws or new postulates, and these postulates bring in new variables which we need to incorporate to describe the energy conversion processes. And what are these variables? We'll see during the course of our study. So we'll see that different laws of thermodynamics will introduce these variables. So the zeroth law will introduce temperature, which is otherwise not known in mechanics. Then the first law will introduce internal energy as a new variable to describe the system. Then the second law, we'll see later, will define a new term, that is new variable, that is entropy. And the third law will not introduce any new variable, but it will put restriction on the permissible lower limit of temperature that is introduced by the zeroth law. So in this course, we'll study the laws and then apply them to analyze energy conversion processes. And these laws are required because we need to have some additional variables to describe the energy conversion processes, because we have done temporal and spatial averaging due to macroscopic measurements, And to compensate for that, we need to invoke new variables so as to define the energy conversion processes. And that's why the laws of thermodynamics are required. So from now, we'll work only with classical thermodynamics approach, and we'll not invoke the microscopic viewpoint in our analysis.